Okay, so for the second installment of the video series on Riemann sums, I wanted to kind of go over, remind you a little bit about where we started yesterday, but go just a little bit further. One thing that happens frequently, because these problems are, frankly, they're kind of tedious to do a lot of those. Again, the more rectangles, the more tedious that becomes. Sometimes you're not actually asked to completely solve. Sometimes you're simply asked to sort of quote unquote set it up. Meaning, if you wanted to take that extra little bit of time, you could go execute and get that, but turn it into a fairly trivial question. So what we're going to do is just take a look at a couple of questions here. So I just thought we would set up a couple of those things and call it good here. So let's imagine we had some simple cubic function here, and I want to find the area on the interval 1 to 4 with 5 partitions. So keeping in mind, one thing that you should be aware of is that sometimes we can actually find this where all of the partitions are not of equal width. Maybe we make the first partition 1 unit wide and the next partition is only 1/8 of a unit wide. That doesn't typically happen. Normally, we would just do b minus a over n, which in this case would be 3/5. So each partition in this case is going to be 3/5. So in this case, we're going to have 5 rectangles, each of those rectangles being exactly 3/5 wide. Now, if I'm going to do a left side Riemann sum, then I'm going to do f of 1 plus, now if I move over 3/5 from 1, I'm going to land at 8/5. If I move over 3/5 again, that would be 11/5, and then we can kind of see how this works. 14/5, there's 1, 2, 3, 4, 1, 2, 3, 4. We need to go one more here, 17 fifths. And keep in mind, if we went one further, that would be 20/5, which would be 4. But I don't need to do that because on the LRAM problems, remember, when you have your story, one of those things extends and you don't actually hit the endpoint. Now, when we deal with MRAM, that's a little bit harder, and I did that on purpose because we're still going to have rectangles of width 3/5, but we're not going to hit at 1. We're not going to hit at 8/5, not the left side or the right side. We're not going to hit here. We're going to hit right in the middle. So right in the middle of 5/5 and 8/5 is actually 5 and 8 is 13/5. So that's 13/10. So that would be, I don't know why I put a pi in there. I guess I was just doing trig with my other class. That'd be 13/10. And keep in mind, if I move over 6/10, that would be 19. And then 25/10. I did the pi again, didn't I? I don't know why I've got that in my head. I guess it's just because the other class. And we continue on until we exhaust the story and not hit a pi again. And then we're sitting at 37/10. And keep in mind, I can't go any further because that would go beyond, but I can also see that there are exactly 5 of those. And this is something that if you took the time you could get, but I'm not going to require it. Now, trapezoidal rule was kind of interesting, because what we learn in trapezoidal rule is, unlike the left side where you use the left but you leave off the right, what we're going to do is we're going to use the left side and cut it in half. We're not going to cut the second or the third in half. We're just going to keep them going all the way up to the end, but we use half of the first and we use half of the last. And keep in mind, as we have discussed, each of these is okay in its own right, but the trapezoidal rule is actually, generally speaking, considered one of the better approximative methods. And the only difference is, instead of ignoring the first or ignoring the last, we just take half of the first and half of the last, and that actually ironically gives us a pretty good estimate. So here's a little problem where we're going to go a little bit further. Now, in this question, what we've got is, and this actually happens in real life scenarios quite frequently. So we're going to use some data, and this I made reference to earlier, that we have this data, and it's like, let's say it's a scientist that's actually taking a look at some data, and they wrote it down at different values. But this particular scientist was not very careful. You'll notice that my first partition is 4 units wide and then 4, and then whoops, they jumped in on there, got 2 units, and then they went, 3. It's a little inconsistent, isn't it? So again, when we do left side Riemann sums, what's going to be interesting is we can't set it up like we did over here where we just say, hey, well, all of the bases are going to be the same because these bases change. So my first partition is 4 units wide and its height was 14. That went from here to here. My second partition from here to here is also 4 units wide, but on the left side, its height is 7. My next partition from here to here was actually only 2 units wide, but at its left edge it was 11. Then we had our final partition, which was 3 units wide, and its height was 16. And I kind of did this already. This total height in this particular story would be 154. Now, when we do our RAM, it's kind of the same idea. We still have a partition width of 4, but we're going to hit on the right side, not this one. So we're going to ignore the 14. Then we have our second partition here, again, width from here to here of 4, but we're going to hit at the 11. Then we have our width of 2, hitting at the right edge, 16. And then here, a partition width of 3, hitting at the right edge, 20. And this time I got 164. Now, what should not surprise you is what's going to happen in this next rule. The trapezoidal sum was always supposed to be this, but the kind of weird part, remember, if we just found the average of these, you would actually get 159. But let's just imagine we didn't know that. So in my first trapezoid, I take base 1 plus base 2 divided by 2 times its partition width, 4, plus base 1 plus base 2, 18, divided by 2 times its partition width, plus base 1 plus base 2 times its partition width, and base 1 plus base 2 divided by 2 times its partition width, 3. And crazy enough, it actually does work if you go through the process. Now, interestingly enough, sometimes we do something that's a little bit strange in that we don't actually ask for it that way. Let's just say you don't need a tremendous amount of accuracy. You just want something. And so in this one, MRAM is kind of weird. And when you do it from data, this is kind of strange. This is going to be one of the worst estimators you've ever seen. I'm just going to look at these two right here. And I'm just going to say, hey, when I look at that partition width is exactly 8 units wide. And the middle value is a 7. And then this one right here was 5 units wide and a decent estimator. Now, this was not perfectly midpoint, but it's close enough. And it was at 16. Well, if we put that all together, I think that's 136. Now, that's not great, but honestly, that was pretty fast. And if all you need is a quick estimator, it's not too bad. Now, the last question that I wanted to go over was one of the very first full-blown AP questions that I wanted to do with you. So we have a rocket here that has a positive velocity. So keep in mind it's going up. And keep in mind velocity is a vector. It could be up, it could be down, positive or negative, right? So the velocity of the rocket is done here. So as it's going up, of course, the velocity is increasing. It's, trying to move up. But you're also noticing that the velocity went up by 9, and then it went up by 8, then 7, then 6, etc. So it is definitely getting faster and faster and faster, but the rate at which it is getting faster is sort of decreasing. So let's find the average acceleration over this time interval. So really, acceleration is change in velocity over change in time. And we know that acceleration is not a constant. We kind of looked at that already. But if I find the velocity of 80 and the velocity at 0, when we find out how much that velocity changed, which of course 49 minus 5, or 44 meters per second is how much it changed. And the delta t is going to be 80 minus 0, or 80. And so I ended up getting 11 over 20 feet per second squared. And that would be the average acceleration over that interval. Notice that it's not the same all the way through, but that's an average value. Some places a little more, some places a little bit less, and that's awesome. So we'll go on to part B. And I've made reference to this here and there, but this is saying, hey, let's go ahead and try to find the area under this curve from 10 to 70. So in other words, just this portion of the graph from here to here. So we have some extra data, but we're going to ignore 0 and we're going to ignore 80. We're just going to look at that portion in the middle. And it's asking us to do something a little bit curious. It's asking us to use midpoint Riemann sums on that interval. So with 3 subintervals. So if I were to break this into 3 chunks, one of those chunks would be here. One of those chunks would be from 10 to 30, one is going to go from 30 to 50, and one is going to be from 50 to 70. So we could say then that the integral from 10 to 70, or the area under that curve, is approximately the following. So this partition width right here is 20. This partition is also 20. This kind, we have the same partition width every single time. And we could see that the value in the middle of these two would be V of 20, and then V of 40 in the middle one, and then V of 60 in the last one. Now, I know that some of you would want to jump right in and just use the values, and you can, but I wanted to show you where it's coming from. So it was 22, 35, and 44. And then what happens when we put all that together is we get 2020. Oh, that's almost like a bad word now. And this was made in 2006. They didn't even know how bad 2020 was going to be for people. So, but if you look at the units, remember the units were feet per second multiplied by seconds, and so that gives me feet. So that would actually tell me how far the rocket has moved. Now, it doesn't tell me where the rocket is, it just says the rocket has moved up. Remember, vectors, they matter. So the rocket was going up, and it went up 2,020 total feet. Now, in this particular case, if we wanted a better estimate, I could go ahead and do the same thing. Now, by the way, this is not what you would have answered on this AP test. But again, keep in mind, we could have done something a little bit better. Every one of these partitions is exactly 10 units wide. So if we had done, let's say, a trapezoidal sum, I'm wanting to make sure you've got that down. So the trapezoidal sum, we take the first one in half, we take all of the second, third, fourth, fifth, sixth, seventh, except we cut the last one in half. And so the area in here, by simply just adding those values with their partition width, would give me a far better result than this one. And it really was not particularly a lot of effort to do so. So that's a second look at Riemann sums, but looking at it through the lens of some data values. Just to understand, we can do the same thing that we did when we had an equation, but in fact, the data values just kind of make it easier. I hope that was a good lesson for you. You'll have a few problems to do, kind of going back and forth between equations and data, and we'll be back soon. All right.